Okay, Harley. I kind of told a little fib there. You know, it's kind of like when Mr. B goes, "Oh, let's run that just one more time," and one more time turns into five times. I told you there would be only two videos before we started going over homework, but there's actually going to be three videos before we start going over homework. And I'm going to talk about in this video the ratio test and the divergence test. Okay, because they can be useful, they're just not always useful. Okay, so the ratio test, we use the ratio test to determine if a series is convergent or divergent. It's just sometimes it doesn't really help us a lot, it's inconclusive. A lot of times the ratio test is works real well if you have factorials, if you have an n factorial in there, because you can do the n plus 1 factorial, and you know that's really n plus 1 times n factorial, and then the n factorials cancel out. So the ratio test looks pretty good when we use factorials. It's not always great, but it's good to have that ratio test and the divergence test in our little bag of tricks that we may need to pull out and go, oh yeah, we can use this here and it actually works. Okay, so if I'm talking about the ratio test, what it says is, if I have this series and I'm just not sure if it converges or diverges, and I'm trying to prove, of course, whether it does or not, I can try the ratio test. And we're actually going to use this, not the ratio test, we're going to use the divergence test on part of our homework. So the ratio test says that the limit as n approaches infinity of the absolute value of a sub n plus 1 over a sub n, if that is less than 1, then that series will converge. Okay? It also says that if I take the limit as n approaches infinity of the absolute value of a sub n plus 1 over a sub n, and that winds up being greater than 1, then it will diverge. Okay, those are very helpful. It's just sometimes we have the last scenario where we have the limit as n approaches infinity of the absolute value of a sub n plus 1 over a sub n, and it actually equals 1. And when that happens, we say that is inconclusive, and we have to try something else. Okay. The other little part of this video is actually the divergence test. Okay. And it is helpful, but it is not as helpful as the ratio test, of course. What it says is if we have that series and we take the limit of that series and it doesn't equal 0, then the series will diverge. Okay? But if it does equal 0, that doesn't really tell me anything. The series could diverge or it could converge. Doesn't necessarily mean that it does converge. So that's why I say it's not as helpful. It only is helpful if it actually doesn't equal 0 and we know it diverges. So the formal definition is the limit as n approaches infinity of a sub n. If that does not equal 0, then the series will diverge. Okay, and we actually do have one on the homework problem where that happens. We get, I think it winds up being 1/3, and it's like, okay, so it didn't equal 0, so then it's going to diverge. And that was like on absolute convergence or something. And then we went ahead and tested it by the alternating series after that for conditional convergence. But anyway, the other part of the divergence goes, okay, well, let's see if the limit as n approaches infinity of a sub n actually equals 0. Then does that mean it will converge? Nope, it does not. What that means is it's pretty much inconclusive. But we say then the series will diverge or converge. Okay, and lots of times my calculus peeps start off with that divergence test and they're just going to prove that series real fast and they get equal 0 and they want to say converges, and we can't really say converges because it's still kind of up in the air. Okay, so anyway, that is our divergence test and ratio test.